If you watch the sky at any hour of the night in any season, you'll notice that all the stars slowly shift throughout the night, except for one. The North Star, also known as Polaris, or by names like Simul, no matter when you look, seems nailed to the sky, standing in the same place and always pointing north. This becomes far more obvious in astrophotography we call star trails, or in time-lapse video. Photographers fix their cameras in place for the whole night, while the camera automatically and continuously photographs the sky. The resulting images are truly mesmerizing. All the stars appear to dance in a marvelous pattern around the North Star. But have you ever really thought about why this star is fixed and how it's able to point north all the time? To answer that, before we talk about the North Star, we need to know that the motion of the other stars is a relative motion. In other words, of course the stars in the sky aren't actually moving or shifting that fast. Because Earth rotates, we fall into the illusion that they're the ones moving. You've likely experienced a similar effect if you've ever traveled by train. When you're looking at another train in the station, your brain has trouble figuring out which train is actually moving. The constant, non-accelerating speed of Earth's rotation creates a similar effect when we look at the stars. Obviously, to find the North Star, we don't need to watch for a whole night to see what the other stars are circling around. There's a much easier way. So let's first learn how we find the North Star. Although finding it in the sky is quite easy, because of a lot of misinformation about this star, many people end up mistaking other objects for the North Star. So let's immediately clear away some widely believed misconceptions so we don't get confused. First, contrary to what many think, the North Star is not the brightest star you see in the sky. In fact, it's the opposite. On the list of brightest stars, Polaris only ranks about 48th. That's why you may not spot the North Star right away in a place without light pollution. Along with that, because there's a widespread belief that the North Star is the brightest object, lots of people mistake the bright planet Venus that appears after sunset, also called the evening star, for the North Star. Of course, Venus appears in the west, the direction where the sun sets, not in the north. Also, the North Star's other name is not evening star. Evening star is just a popular nickname for Venus. So if the North Star isn't an especially bright object, why do we say you can find it easily? Because we have a very practical method that always works. When you look at the sky, the easiest and quickest constellation to recognize is undoubtedly Ursa Major, the Big Bear, which people commonly call the Big Dipper or the Great Ladle. And it really does look like a giant dipper in the sky. If your sky is clear, after a brief scan you can find this dipper quite easily because it takes up a large area. Once you've found the dipper, focus on the two stars at the far edge of the bowl. Now take the distance between those two stars as one unit. Then, moving in the direction those stars point, go 5 of those units. There you'll be greeted by the North Star, Polaris. Of course, to make these observations stick, you need to observe often and also learn the other constellations and objects in the sky. But I know most of us live in cities and can't see the stars because of light pollution, so we don't get the chance to really learn the sky. And that's why I have great news for you today. For 7 years now, every year in Antalya's Olympos region, we've been holding Turkey's largest astronomy festival, the Olympos Sky and Science Festival. This year, the festival will take place on August 11th, 12th, 13, and 14, and as the Astropera team, we'll be there serving as observing guides. In other words, this time we'll introduce you to the sky not on a computer screen, but hands-on, far away from city lights. I'll share a link with all the festival details in the video description and in the comments. Now let's explain why the North Star appears fixed. There's a very simple reason Polaris always seems stationary. As you know, Earth rotates about its own axis. That is, we can talk about a rotational axis. If we were to describe this rotation axis with an imaginary line, Polaris lies in the direction that line points. In other words, because the North Star happens to lie along the direction Earth's axis points, we always see it as fixed. Therefore, the farther any given star is from the North Star, the larger the circle that star will appear to trace around Polaris. In fact, the North Star itself isn't exactly on the axis's direction either. There's an angular difference of about 0.736 degrees between the pole point and Polaris. But especially to the naked eye, that's small enough to ignore.
At this point, we should also say that the North Star is a star visible only from the northern hemisphere. So another question comes to mind. In that case, can people living in the southern hemisphere not see the North Star, Polaris, at all? The answer is yes. There's no way to see Polaris from the southern hemisphere. And yet we know that ocean-going navigation in the southern hemisphere started as early as about 2500 BC, long before the invention of the compass. So how did explorers, and especially sailors living in the southern hemisphere in the past, find their directions? Or forget about 2500 BCE. Today we see star trail photographs on the internet taken from southern hemisphere countries. So what do we make of those photos? In those, we also see a fixed point with stars circling around it. Does that mean there's a fixed, direction-giving star in the southern hemisphere, too? The truth is that in the southern hemisphere there is indeed a star located almost on the same axis as Earth's rotation, so it appears relatively fixed. Considering that there's a star in every direction in the sky, it wouldn't be surprising if a star lay close to the direction of the South Pole. But here the main point is how bright the stars in that direction appear to us. We in the northern hemisphere are lucky. Although the North Star isn't extremely bright, with a bit of observing know-how and with the naked eye we can find our pole star pretty easily. People in the southern hemisphere are a bit less lucky. Their pole star, Sigma Octantis, sometimes called the South Star, is about 25 times dimmer than our Polaris. So instead of trying to focus on Sigma Octantis to find their pole, people in the southern hemisphere historically used brighter stars and constellations they knew to be close to Sigma Octantis to determine direction. Because, as we said earlier, stars near the pole star trace smaller circles around it. The smaller the circle, the closer to the pole point that star lies. We said the North Star appears fixed, but that's really only for time spans of a few centuries or a few millennia. In reality, the positions of the stars in the sky do change, but mostly not because of the star's own motions. Rather, it's due to a quirky motion Earth itself makes, called precession, Earth's wobble. In other words, as Earth spins on its axis, it also performs a wobbling motion similar to a top as it begins to slow down. Because Earth's wobble is periodic, it means that the direction in the sky toward which Earth's axis points is constantly changing. We know Earth completes one full precessional cycle in 25,800 years. Therefore, about 13,000 years from now, Earth's pole star won't be Polaris. It will be Vega, one of the brightest stars of summer. And since Vega is the fifth brightest star in the sky, people 13,000 years from now won't have as hard a time finding their pole star as we do. Maybe we don't have much trouble today either, but for them it will be even easier. Of course, up to this point we've said all these observations are due to Earth's motion, not the star's own motion. So you might ask why we don't account for the star's own motion. Naturally, all stars, including Polaris, do have real motions. Indeed, all the stars we see at night belong to our galaxy, the Milky Way, and they move through space. However, they are so far away that we can't easily see how they move relative to one another. To reinforce this with another example, imagine you're driving down a highway at 120 kilometers per hour. At that speed, the streetlights or power lines along the roadside whip past you quickly. But when you look at a distant mountain, you'll notice it hardly seems to move at all. In reality, both the faraway mountain and the power lines are changing position relative to you at the same rate. But because of distance and perspective, the mountain seems to approach much more slowly. Roughly speaking, the farther an object is from you, the less it appears to shift from your viewpoint. Even the closest stars to us are at distances measured in light years. So although they are truly moving, without professional measurements, it's impossible for us to notice. That's why, due to their distances, the apparent shapes of the constellations we see in the sky have changed almost not at all for thousands of years. In other words, it's fascinating, but we're still sharing essentially the same sky with people who lived long ago, our ancestors. We see almost exactly the sky they saw thousands of years ago, the sky they often couldn't fully explain, wondered about, and drew inspiration from. And that, once again, reminds us how short a human lifetime is compared with the motions of stars across the vastness of space. We'll see you in a completely different corner of the universe in the next video. Goodbye.